This problem reads, the drawing shows a top view of a square room. One wall is missing, and the other three are each mirrors. From point P in the center of the open side, a laser is fired with the intent of hitting a small target located at the center of one wall. Identify 6 directions in which the laser can be fired and score a hit, assuming that the light does not strike any mirror more than once. Draw the rays to confirm your choices. So I adjusted a few things. I made this picture from the book transparent so I can have this grid in the back. I made the grid finer so I can see better, and I prepared some arrows here for which should depict the laser direction, and then I put a protractor here, and I put these optical axes here as dashed lines. This, of course, is kind of a neat exercise in order to illustrate the most simple law in physics that you can imagine, and that is the law of reflection, which is the angle of incidence equals the angle of reflection, and that holds for all kinds of mirrors. In this case we have flat mirrors, but later as you get into concave and convex mirrors, that law still holds. It looks a little bit different when you get into concave and convex mirrors, but keep in mind it still holds, and I have another example coming up where I will try to show that. Alright, so let's get this going here. And the first one, of course, is I can just go from this point here and hit the target directly. There we go, and then I can even write that the angle is 45 degrees here. Let me just see if the problem actually asks for that. Identify, doesn't specifically ask for that, so I'll see what I do. Okay, then of course it could hit the wall on the left, midway here, or quarter way up, there. Actually I have to think, nope, that's not going to be right. Nope, of course not. A third of the halfway up here, because then I'm going to copy and paste it and turn it around. There we go, because then it will go right there, and then of course by symmetry it will extend up there, and with the optical axis it's right there, and then I can take the protractor and put it on it, and that would give me an angle of kind of like 160 degrees from the right hand side. Again, I don't know if they actually ask about that, and if I write that in here it's almost kind of like an overkill. 20 degrees from down here, 160 degrees from all the way around. I could calculate that it would be the inverse tangent of 1 over 3. When you look at the big squares that I have, 18 degrees subtracted from 180, so actually 162 degrees. But I'm doing this more or less casually, just looking at this one here. So let's see, it should be, if I hit this one here up here first, then it should be just in reverse kind of. So what I could do is I could put that arrow there, then copy this one here and flip it, and then again that would be symmetric, and it comes from the original point. And then my optical axis would be here, and again we can see that the angle of incidence equals the index equals the angle of reflection, and the angle here, well, that would be the inverse tangent of 3 over 1. Kind of looks like 60 degrees, right? 71 degrees, 72 degrees rounded. So so I could put that. I think I'm really running out of space down there, so I'm just going to put it down here, 70 degrees, 72 degrees for the red one. Again, I don't think they asked that actually in the problem. Okay, and the next one I'm going to do is actually going to be really easy. It's going to be the one that is sitting midway here, and then it's going to hit midway here, and then it's going to hit, of course, midway over there. And then of course I can see that I have an angle of 135 degrees for the green one, and the optical axis is over here, so the 45 degrees equals the 45, and the other one is over here, same deal, 45 and 45. Okay, two more. Okay, I think these were the easy ones. So now, let's see. I mean, I can identify easily the next one. It's going to hit here, then it's going to hit here, and then it's going to hit here. That was still easy, but the exact angle is going to be a little bit harder to explain. What I figured out is that as it goes from here to the right, it traverses half of the square, then it traverses 2/2 of the square to the other side, and then back over here again 2/2 to the other square. So as it traverses here the square 2.5 times, that would mean 5 of its halves, and that also means that each time as it goes up here it's 1/5, 1/5, 1/5, 1/5, and the remaining fifth. And that's how I figure out what my angle is. It's going to be simply, well, now it's simple, the inverse tangent of 1 over 5, which gives me an angle of 11.3 degrees. So let's see if I can do that. And before I actually do that, I will make a couple of copies of these. They magically appeared there because I had stopped the recording, and then when I put it there, it's on top of my protractor. I cannot move it. Alright, so I'm going to try this here at 11, kind of right there. So there it hits. Okay, now the other one. To make that extra long. Yeah, there it goes. Okay. And then another 2/5 up, so boy, oh yeah, my squares I believe do divide into fifths, so I have 3 little squares up. Now I'm going to have an extra 6 little squares up, so it should be actually right there. There we go. And then this one here. Oh yeah, I just noticed that my squares are actually divided into 5 parts, so that makes it actually easy to draw. And there it is, and now I can hopefully move the protractor. There we go, and then again here are the optical axis. There's one, and there's one, and as I said, with these fifths that I have to go up there, it would be the inverse tangent of 1 over 5, and I come up with around at 11 degrees for this blue or turquoise one. And again, you can see that the angle of reflection is the same as the angle of incidence within my abilities of drawing accurately. Okay, and on the last one, I think it's the most difficult one. I would hit here somewhere, then over here somewhere, and then it reflects over here somewhere, and then it goes there. And actually, I have to admit, I mean, this one I can figure out myself that it does something like that, but I have to admit that I had to look actually at my solution manual to figure out what the exact angle is. It says 31 degrees. So again, I'm going to copy these here and show you in a moment. So these magically appeared here. So at 31 degrees, if I'm able to grab it again, I'll make it longer to begin with. There we go. That I would have to go up 9 little squares here. Put my optical axis here, and then when it's being reflected, I go up right here 9 little squares and another 9 little squares to the other side there, and I still got that correct. Okay, then my optical axis is here, and I need 4 of these. And then I have to see, how do I do this? It goes through here and there. This is really tough to see. I really have to kind of eyeball it here. And then my optical axis is here. And you can kind of see at this point, of course, the whole thing has just become a game. Starting out with looking at the law of reflection, and then kind of, well, yeah, it's a game kind of right now. And then there it is. And this, as I said, this last one over here was kind of eyeballed, but if we look closely, yeah, there should be still angle of incidence equals angle of reflection. And as I said here, I had to look this up here, so 31 degrees for the black one. And while the others I was able to calculate, on this one here I got too lazy to do so. I'm sure there is a way. This problem reads, a concave mirror with a radius of 56.0 centimeters is used to project a transparent slide onto a wall. The slide is located at a distance of 31.0 centimeters from the mirror, and a small flashlight shines light through the slide and onto the mirror. How far from the wall should the mirror be located? The height of the object on a slide is 0.95 centimeters. What is the height of the image? And how should the slide be oriented so that the picture on the wall looks normal? So I took this diagram here from the book and I added a few things like this flashlight, and then that's the only slide I could find, I guess, and I actually adjusted the size of it so that kind of this diagonal of this small slide here is similar to this one here, and so that when it's projected that this one here is similar to this one here, so kind of the scale is similar respectively. The problem here gives me new numbers and it doesn't necessarily go with this image, but in principle I believe you get the idea. It doesn't say where the flashlight is supposed to be. Well, when it comes to the mirror equation, all that's important is where the object is. So if I have the flashlight here or here or here, it still gives me the same image over here. Okay, this applet here I will do later, and even before I start this problem, I wanted to show the law of reflection and a few examples. So these are also from the book, where I have a light ray hitting a curved mirror, in this case a concave mirror, and then it's being reflected, and it shows that the angle of incidence is the same as the angle of reflection. And in fact, if at this point here I'm putting a line tangent to the mirror itself onto that particular point where it's reflected, and then I put an optical axis which is perpendicular to that surface piece there right here, then we can see that, yeah, the law of reflection the easiest law that there is obeyed. And what happens on a curved mirror is that for each little point where the light hits, at whatever angle it hits, we would have to draw a particular tangent line on it. Then that gives us the optical axis from which then we can draw the reflected angle. And down here I'll put a few more examples. I'm not going to do all of them, but again I have here at least I try to move this one here, make it just right. Okay, so here at this point here, I have that tangent piece here on the curved mirror, and here's my optical axis, and because it hits right on the optical axis, it comes right back. Then for the other piece here, let's see, ever so slightly of a tilt, right? And again, I have here the optical axis, and that already kind of looks like perpendicular to it. And then here I have a small angle coming in and the same small angle coming out. And then for the other piece down here, freehand drawing worked pretty well. And again, the optical axis is perpendicular to it. Trying to draw it as accurately as I can. And then again, I have the incident angle being the same as the reflected angle. So overall, again, when it comes to a curved mirror, you would have to put a tangent line on each single part of that mirror, draw an optical axis, and then use the law of reflection. Angle of incidence equals angle of reflection to come up with the reflected ray. Of course, that seems to be quite a bit of work, and fortunately there's a shortcut, and that shortcut is that we use special rays here. So here's an object, and from that object rays go in all kinds of directions. So just like I show here, they go in all kinds of directions. Of course, we're not interested in the rays that go over here because they're not hitting the mirror. We're interested in the rays that do hit the mirror. Okay, of these we have gazillions of light rays that are hitting the mirror, and it would be just too much to do this here. So we single out a few. Well, the mirror equation shows us that a few particular rays, such as the one that is parallel to the optical axis of the middle of the mirror, this one here, will go through the focal point when it's reflected. So this parallel one here, parallel to this optical axis, will go through the focal point. And then if in hindsight we draw this one here like I did earlier, the tangent line on the mirror and the optical axis, we can see, yeah, hey, that's actually true. Another one would be a light ray that is actually not drawn this way, but we're starting with the center of the mirror. You know, the mirror here has a certain radius, and this here would be the center of that radius, and the focal length for a curved mirror, in this case a concave mirror, is half of that radius. So that's where the C comes from, that's where the F comes from. So if we start here and draw a line first here, and then we extend this line now towards the mirror, then that one will come right back to it. Which makes sense to it too, because seen from the center, a radius vector hits the circle, and there we have the tangent line that it hits it perpendicular. And then of course is reflected right back. And the third special ray that emanates from the object that is easy to draw is the one that goes through the focal point first, hits the mirror, and then comes back parallel to this original optical axis. And again, if we draw this one here, this tangent line here at this point here, and make the small optical axis, we can see, yeah, angle of incidence equals angle of reflection. This one here and the first one that I talked about, this one here, they're symmetric to each other. This one is parallel and then is reflected through the focal point. This one shines through the focal point and then is reflected parallel. That's what I mean by symmetry. Okay, so in any case, that's how we then can figure out where the real image comes out over here where these three are joining. Of course, technically I only need two because two light rays will cross each other, but the third one is there to confirm that the two are doing that respectively. It's available anyway, so I might as well draw it in. And again, out of these gazillions here, there are these three special rays. When we get into lenses into the next chapter, we will see that it's basically the same three rays again when it comes to lenses that are the special rays. We can do any of the others, but they would be quite a bit harder to figure out. These ones are the easy ones. Alright, let's get back to the problem. Actually, let's start the problem. So let's see, I'm going to move this out of the way. I probably need the space here, and let's see what they tell us in the problem. Concave mirror, R equals 56 centimeters. R equals 56 centimeters. That tells me right away that the focal length is 28 centimeters. Because it's half the radius. That focal length is a positive number because it's a concave mirror. The object distance is given as 31.0 centimeters, and they want us to figure out what the image distance is. And then later on, the magnification. Well, all we need for that is the mirror equation, which says 1 over dO plus 1 over di equals 1 over f. And this one is called the mirror equation, and in the next chapter we'll find out that the thin lens equation looks exactly the same. So between mirrors, curved mirrors and curved lenses, convex mirrors, convex lenses, convex mirrors, concave lenses, there are a lot of similarities. This is one of them, and then there are a couple of things that are flipped around because, for example, we will see that the convex lens does the same thing as the concave mirror, which we're using here, which is to produce a real image. So anyway, this is our equation, and we're supposed to figure out what this one is. So algebraically solve for this one here, 1 over di equals 1 over f minus 1 over dO. And then of course that would have to be inverted. So it's this one here again, except I have to put parentheses around it and invert it. And when I do that and plug everything in, then I have centimeters here, I invert it, which means that centimeters goes back to the top, which makes sense because it's a distance here in centimeters. Just leave it all in centimeters. That's more convenient. You will see that in any one of these mirror and lens chapters that all the numbers are given, virtually all the numbers are given in centimeters, and we might as well stay in those as they're easier to handle than converting them to meters. Oh yeah, one more thing here, which is the magnification. So all I need for that is grab the magnification, which says m equals negative di over dO both of these numbers, you will see that the di will come out to be a positive number, and that's because when you look at the 28 here and the 31 here, as you subtract 1 over 31 from 1 over 28, you will get a positive number here because you subtracting a smaller from a larger number. So this one here is going to be positive, this is positive, but with the negative, of course, the whole thing is going to be negative. There are no units on this one here, so you come up with a negative magnification. What it means is that negative is that the image is upside down. So if you want to show a nice slide of some people or something, this one here looks kind of like a clock on there. Whatever you want to show, make sure that you put in the slides upside down, because here with the negative they're turned around so that they show up right side up. The magnification here, well, you have to compute that and see how much bigger it actually gets. Oh, and then I just noticed, yeah, in the problem actually it says that we're supposed to determine the height, but that's no big deal. After I have the magnification, I just say that the image height equals that magnification times the object height, which was given here in the problem as HO equals 0.95 centimeters. And then again, because the magnification is already negative, meaning that it turns the image upside down, that is also a negative, meaning that it points downwards. So, and that one will be in centimeters, because this one is multiplied by magnification with no units. Okay, and lastly, I wanted to look at the applet that I posted there. Pretty much find applet, let's see, I think I just Google optics applets in order to find something, and I chose this large simulation, and then I choose the mirror here. There it is, and then I push it somewhere over there, and then it doesn't allow me all focal lengths, but notice down here at the very bottom right you can see the focal length. So I cannot do 28 centimeters, but I can do 2.8 instead, and then some times 10, and then I choose an object, and they always give me this kind of error here anyway, and then I actually have to adjust the mirror here so I can easily measure this. For example, I go to 7 centimeters, you see it bottom left and bottom right, 7 centimeters, and then this one is supposed to be 3.1 centimeters away from that. That's what the problem says, right? So I put this here at 3.9, and there, now I have redone the problem in this kind of applet, and we can see these rays here. Here's the parallel one, it goes through the focal point. Here is the here's another one that actually goes directly to the middle of the mirror and then is being reflected right here, and the one that they left out is the one that goes over here and then comes right back, and the one that goes to the focal point first actually misses the mirror. So if they had extended the mirror here, then it would go over there somewhere. But there's another big problem with this one. The numbers in this particular problem are such that this applet cannot accommodate them. I tried the following. Let me show you. I quartered the focal length and so on. So let me show you. This is kind of trying to fake it to make it work. I'm going to push this out to 7.75. You can see that on the lower left there's a 7.75. I'll let you know in a moment why I did that. And then the focal length, instead of using 2.8, one moment. Actually, I do the focal length first. So of using 2.8, I take a quarter of it. So I take 0.7. There we go, as a focal length. And now I push it to 7.75. And then I take a quarter of the original object distance. And so a quarter of 3.1 is 0.775, that is. Oh yeah, so I actually should put this here to 7.75. 775 actually. There we go. It's close I can get. So this one ends up at exactly 7.0 there. And even then I have a problem that this is kind of way off here, so it's way over there, and we can see that these two come together, and here's this real image of this little arrow. So apparently we come up with quite a magnification on this one, and we come up with quite some image distance. So keep that in mind. You come up with a relatively large centimeters for the real image in the actual problem. And again, what I did here is, in order to kind of fit it into this applet here, is to quarter the focal length and quarter the object distance, and that actually I noticed when I calculated it also quartered the image distance. And again, the real problem that prohibits me from doing it accurately in this applet is that this image distance here is so large. So from this problem itself, the image distance is so large, yeah, it just cannot fit onto it. If had I chosen a different kind of problem, then I could have put it on the applet. But I wanted to do this one here because it's kind of like a slide projector, right? And the image on the slide projector actually does become quite large, and you will see it's going to be in the neighborhood of a 10 times magnification or so.